Hey everyone, there we go. I was turning off the music in the background. We got some questions. Which one should we do? Taylor to start, and Blake, what should we do? We got some questions here to start. Which one should we do? Put in the chat which one you want to do. I see Taylor. Which one do you want to do right there? And so you've got the margin of error one. And Blake mentions the data analytics. We could do the data analytics. First person to put a question in the chat is the one that we do. Which one should we do? If you're here in the chat, feel free to say hi. First question in the chat is the one that we do. Data analytics or which my Pearson question shall we do? Let me know which one you want. And let me get my Pearson up and going. Chop the 13. Hey, Lachey, good to see you here. Which question should we do? If you're here, you get to pick the question. See, Blake has one, Taylor has one. Which one should we do? Let's see. Good to see you here, Ford. What's up? Good to see you. Just chilling out. Pumping chairs. Let's see. So an insurance company checks. Let's take a look at this right here. Insurance company checks. What do all these questions boil down to? All of these questions. Yeah, thank you so much, Ford. Good to see you. Yeah, and I was like, which semester? You got to give them some advice right here because these questions are going to boil down to knowing your notation. So who can help out here with some notation? Ford, good to see you. How's your semester going? What are you up to? We got to grab some notation right here for this problem. And that's going to help us solve it before we even read anything. What is the notation? Lachey, do you know the notation? Do you know your notation for this problem right here? It's going to help us solve this before we even do anything. We need to know what we're solving. We're trying to figure out a confidence interval for the true proportion. So what is the notation right here? They went out and talked to, yeah, I'm a combinator. I love it. Oh, of course.
Notation, brother.
Leo knows all the notation. We give shouts to Leo all the time here. Blake knows about Leo. He knows of the famous Leo. Got to know the notation. Gotta know it all the time. Hey, Meredith, good to see you here. Just let me know what you want to work on. We're working on this 201 problem right now. And so we have 577 accidents that were sampled, random sample. And there were 94 teenagers at the wheel. So probably the numbers. So what is the notation on this? People get tricked on this because we're asking, was a teenager at the wheel? So what is any of the notation? Any of the notation in this problem. Who knows any of it? Only have two things, and it says making 95% confidence interval. So what is any of the notation right here? X over N. Great job, Lachey, right there. We got to throw you some points. X over N. So what is X? What is N? And that'll solve for what, Lachey? 5,000 points. I think you're on the right track right here. So Lachey's pointing out X over N. There we go. And 94 over 577. And that is X over N. And that is equal to what? Like, we can find what it's equal to, but we should know also what we're solving for. This is going to be the proportion of time teenagers were at the wheel in the sample. That is equal to P hat. Great job, Lachey, right there. So that's P hat. And once we find P hat, we find Q hat. Q hat is going to be the complement of P hat. So we just go right here and do 1 minus. Whoop. Invalid input we'll do. 1 minus invalid input. 1 minus 0.1629. There's Q hat. There we go. So there is Q hat. And now we need to know the what. What is that 95% going to be used for? What is that 95% going to be used for? How are we going to use that 95%? How are we going to use that 95%? Because we know what P hat is. We know what N is. There's N. There's, let's put P hat as a different color. P hat is here. And that is what P hat is. What is N going to be? What is that's Z? The confidence level. Great job. So what is the confidence level? What is it? What is the confidence level? Since it's 95%, it's a classic number in statistics. It's going to be 1.96. Make sure to go over here to the David M. Lane applet. I'll put it in the chat for everyone right there. Click the button right here for the second button. Type in 95% and make sure to do between. And you get the number of 1.96 for 95% confidence. So now that we have all of our numbers right here and we know the z-score, 1.96. There it is right there. And now we just plug in our numbers. First thing I solve for is the margin of error. We need to solve for the standard error first. And standard error is 0.015, so it's going to be about 3% margin of error. There it is right there, basically 3%. So that says a decimal right there. Good stuff. Let's see what the question asks. That should be rounded nice and neatly. Okay, so it's 3%. So 13 point, was it what, 2 decimals or 1? So 13.3 to 19.3. I think that's correct. So 94,577, 95%. Check my work over here. Yep. 13.3 to... Oh, wait, it's not going to be... I didn't err on the calculation on the top of the interval. The top of the interval is 19.6. No, it's 19.3. That is 19.3. That is right on the top of the interval because it's 16.6. The center of the interval is 16.29. And so 16 point... or plus this, that's 19.3. 16.29 minus is 13.3 rounded. And make sure it times by 100 for percentage. Explain what this means. Now, what do you need to know how to do for the test? So if you're watching this question for the test, this is super important. And we wrote this down today in class. So this is huge right here. Hey, what's up, Taylor? So data analytics, we could do data analytics next. So you need to know how to interpret this. I am 95% confident the true proportion of times that a teenager is at the wheel is contained in the interval 13.3 to 19.3. So I am 95% confident the true percent, that sounds like proportion, I'm 95% confident the true percent of accidents involving a teenager is contained in the interval, and that's got it right there. About 95% of random samples will produce intervals that contain the truth, and Justin went into that today in class mentioning that. A politician claims that about 1 in every 5 would be what percent? 1 in every 5 would be what percent? So 1 out of 5 would be what percent? 1 out of 5 would be what percent? 20%, great job, Meredith, right there. So do you think that's true or do you have reason to doubt that? You're 95% confident the truth is between 13.3 to 19.3. So do you believe the 20% or do you have reason to doubt that? What would you say, like, that seems believable, or nah, I got reason to doubt that? What would you think right there? Doubt or believe? Hint, press X. What do you think? Doubt or believe? Would you doubt their claim or believe it? They'd be like, that's reasonable to believe, or we're like, nah, we got evidence against that. Because I think the truth is somewhere between 13.3 to 19.3. 19.3. Maybe as low as 13.3% or up to about, not really about, but up to 19.3. So I'd say, if they're claiming 20%, I'd say, I don't think that that's true because it's outside my interval. Anything outside the interval, I'm not really believing. I think the truth is somewhere between 13.3 to 19.3 with 95% confidence. So the confidence interval does not contain The conf interval does not contain, does not, oh, does it? The conf interval contradicts the assertion. The figure quoted by the politician is outside the interval. Right there. Check answers. 100%. We're getting those hundreds today. Doubt. Does he say that for doubt? Mubot talking about some doubt in the chat. So we have right here that is outside the interval, so we would doubt that. Does that make sense, Lachey? Like 20% doesn't really seem that plausible because it's outside the interval. I know it's just barely outside, but that means we just barely doubt it. So we think, I don't know if 20% is true. It's outside the interval, so I don't believe your claim of 20%. So let's do some data analytics. Let's do it. Time for a little data analytics. Mubot pressing X to doubt in the chat. Data analytics time. Stat 201, data analytics. We have data analytics. Which one's coming up? It is due on Friday. Confidence intervals. Okay, it's 2 confidence intervals. Good stuff, what we've been doing in class. Let's take a note right here. Go over a little bit. Data analytics. I need to grab some water. Ay. Let's head over to the screen and do it. So we are with some data analytics, confidence intervals. I might grab some water in a moment. So use the data set stat 201 survey data.jmp. Take a random sample of 300 plus the last 2 of your UTID. For example, if your UTID ends with 23, take 323. For this exercise, assume that we've collected it from this many students. What do you think this relates to? Since we're collecting a sample of 300 something students, we're trying to give you hints. I'll be doing here next, Taylor. You got it? So we're trying to give you hints here. That sounds about accurate, maybe. So we're trying to give you hints when we say, here's the sample size and here's the population size. What condition should that be checking right there? What condition should this be checking right here? So here's the sample size. Here's the population size. It sounds like this is alluding to right here the what condition. Because it says you're going to sample 300 something from a population of 5,374. So what is that alluding to right here? What condition does this automatically make you think of? The 10%, great job, let's share it there for 1,000 points. So automatically we're thinking, hey, they're trying to tell us that we've sampled less than 10% of the population. Okay, and it is a random sample, so we're good on that. We'll check the other conditions coming up here later. Make sure to do this in a Word document. Make sure you type out everything fully and do all your work, please, please, please. So note the population is of interest is stat 201 students, the parameter of interest, and this is huge right here, the proportion of students who think humans will land on Mars in their lifetime. This is going to be very important when writing out your interpretations, and let's go right here, because that's talking about the context, and you're talking about the true proportion, and there's the context of it. So I'm not going to write this out fully. I need to grab some water, I think. But we are talking about the true proportion, and then the context I've highlighted right here. We're trying to figure out the true proportion. Make a 91.5% confidence interval, and there we go, of the proportion of students who think we will land on Mars in their lifetime. Include a short write-up, including the 3 conditions you have to check. Clearly indicate and whether or not each condition is met. And make sure your interval interpretation has all 4 parts. And make sure to give the jump output. You should see the grading down here. If I'm doing this, I would check that I included my name, random sample, and go through and look at each one and make sure you meet the requirements for each of these to make sure you get the full points. Always look at the rubric. So when you're doing this right here, let's go look at some jump output, and we'll grab this data right here and look at how it should look. Here we go. So if we want to figure out what % of students at UT are on campus, we can take the variable right here. And once again, I want to point out, I'm not doing your exact question. I'm doing a little different one. You'd want to start by going to tables, subset, and then take a random sample of 300 plus the last 2 of your UTID, and then make sure whenever you're working on this, you're working with your random sample. That's very important. Make sure to do that, or you'll lose the points for taking a random sample. Now, you want to do your variables right here. So I'm doing very similar work and very similar interpretations to what you'll be doing on the data analytics. So here we are. Analyze distribution. Under Analyze Distribution, you will select your variable of interest. I'm going to look at we're going to look at distance from campus. I'll double click it and click OK. So this is under Analyze, then Distribution, and then click OK. And now we have the analysis. I like to go ahead and click Stack right here to put it in horizontal layout. We could expand this a little bit so it's easier to read. I think you can even change the text. I don't like that label. We want vertical. There we go. Easier to read now. Let's make sure your data looks good. Now we are going to go here and talk about the students on campus, and we want to make confidence intervals, clicking the red arrow, confidence, and it asks us to do something other than a 90, 95, 99%. We want to go in here and put in something like 91.5, and that'll make a 91.5% confidence interval for the students who live on campus. So what are we trying to figure out right here? The true proportion of students who live on campus. I am 91.5% confident. I am 91.5% confident that the true proportion of students who live on campus is contained in the interval 26.4 to 35.4. So do you think it's possible about a third of students live on campus? Do you think it's plausible that a third of students might live on campus? What are your thoughts on that? Look at the interval, and I think the truth is somewhere between about 26.4 to 35.4. Do you think it's plausible to believe about a third of students live on campus? Someone said, about a third of students probably live on campus. Would you say, it's believable? Or would you say, nah, I don't think that's true? What would you say to that? If someone said, I think about a third of students live on campus, would you say, yeah, that seems possible? Or, nah, I don't think that's true. I am 91.5% confident that the true proportion of students who live on campus is contained in the interval 26.4 to 35.4. What do you notice about 1/3? What do you notice about 1/3? 1/3 is in the interval. So since 1/3 is in the interval, I would say that that's believable, that we would believe it, i.e. not reject it for later. If someone said half of students live on campus, I'd say, nah, I don't think half of students live on campus. About a third of students live in the fort too. I mean, it's plausible. The best estimate of the percent of students who live in the fort is 31%. The best estimate of students who live on campus is about 31% too. Interestingly enough, and you look, there was just one student different, and the percentages are very close. And the estimates for the true proportion of students who live on campus and the true proportion of students who live on the fort are very similar too, with 26 to about 35% for both. Quote the numbers exactly when you're doing it right there. Now, when you're doing conditions, actually, I've got them written down a little bit here today. When you do the conditions, you always start by doing condition 1 is random. So the first condition we check is that our data was randomly selected. So make sure your data comes from a random sample. Make sure to communicate that. And I'd even say something like pass or fail when I do this, so that the person grading it, not POIs yet, but I would say pass, and then I would explain why. I think it's a great way of doing it. The next condition we do is the less than 10% condition, also known as the 10% condition. We need to sample less than 10% of the population. So also tell whether or not we pass. I would do that. So do we pass? And then why? Explain why. Now, you have to pause before doing the third condition because the third condition is not always success failure. At this point, we have 2 third conditions to pick from. We'll either do success failure or nearly normal. So the nearly normal condition is for quantitative data, and the success failure condition is for categorical data. So if your data is quantitative, which will be the next one we do, we'll do the nearly normal. And if your data is categorical, we will do the success failure. Now, to check to see if there's at least 10 successes, at least 10 failures, for my problem, I need to do the following. Are there at least 10 students in my sample who lived on campus? Yes. Are there at least, the on-campus one, excuse me. Are there at least 10 students in my sample who lived on campus? So that's actually X. Yes. This is also NP hat. And just to show you, N right here is 312 times P hat. And it solves out. It's just there's not enough decimals. There is at least 10 who live on campus. And then this is NQ hat. If we add up all these values, there's at least 10 who don't live on campus. So I would quote those values. I would say there's at least 10 students who live on campus. Mainly 97 students live on campus. And then 312 minus 97. There's 250 students who don't live on campus. We have at least 10 in the sample who are what we are looking for. and at least 10 who are not what we are looking for. So NP hat and Q hat are both greater than 10. P hat is the sample proportion, that value right there, and Q hat would be the complement of it. So if you want Q hat, you have to take and subtract. There's Q hat, and you could times that by 312 for NQ hat, and you notice we get just down to the decimals the other side of it. 96 plus 216 is going to be 312 right there. So NP hat and NQ hat equal up to N because it's the amount of successes in your sample and the amount of failures. And that is explicitly for categorical data, not for quantitative. You'll see the small change here in a second as we talk about quantitative data. Make sure to check your conditions. So you need in your thing, I would put my name up here at the top. I'd put my output, and then I would put my condition check. And then you need your interpretation. So you need that right there. Could we possibly go over what we need to be looking for doing task 4 on the sport? Ooh, Ella, let's do that here next. We'll do Taylor's question, then we'll do your question. Ella, that's really good right there on support vector machine. I like that. So now we go over to the mean, and the mean question is going to be very, very similar on this. Confidence interval for the mean, which we were doing today in class. So now we want to make a 99.9% confidence interval. This is going to be way more confident, so it's going to be way less precise. When you increase confidence, you decrease precision because you make the interval wider by increasing the test statistic used to create the interval. So I am 99.9% confident about what the expected salary is. We won't do expected salary right here, but we will use our random sample to go in and go here to analyze distribution. And now go to the quantitative variable you want. Make sure to use yours. And let's look here at the age of UT students. Because this is quantitative, it's in blue. So make sure you're doing the quantitative one it wants. And the first condition for this is that this is a random sample. So is this a random sample? Yes, it is. The second condition is we've sampled less than 10% of the population. Make sure to look at the population size and describe whether or not your sample is less than 10% of the population. And the third condition, make sure to pause, is not going to be, don't say it, it's not going to be this one, because we're doing age, for my example, it's going to be nearly normal. Now, nearly normal is a very complex one that has 4 ways to check it. Way number 1 is look at the curve. Way number 2 is going to be normal probability plot. Way number 3 is going to be goodness of fit tests. And way number 4, which we often use, is large enough N. So you can use the large enough N way to check the nearly normal. Let's try that right here. We have a very large sample size. We have a sample size of 312. So if you remember from large enough N, the distribution will be nearly normal for the mean if N is large enough, and we only need, if it's skewed a little bit, a sample size of 25. Even if I say this is pretty skewed, I need a sample size of 100. So the large enough N works the following way. 1, look at the distribution, look at the shape of the distribution. Skewed or normal, skewed, very skewed. And the requirements are 1, put it in order right here, 1, 25, and 100 respectively. So the more skewed it is, the larger N needs to be. So if the curve was normal to begin with, sample size doesn't matter. We're fine. If the normal probability plot comes out normal, which we actually have that in the notes, I think they do a good job of showing it right here. If the normal probability plot comes out normal, which is right here, we're good. It's linear. If the curve looks normal, we're good. If the goodness of fit test comes back greater than 0.05, we're good. And that's way number 1. Look at the curve. Way number 2 is the normal probability plot linear. And way number 3, or does it follow the line, I should say? It's not really a linear relationship, but it follows the line down the center. It does. And way number 3 is the p-value for the goodness of fit test greater than 0.05. We're good. If we do not meet those conditions, we can always use the large enough N, which can be found right here. And we can look at the shape of the distribution, which we would say here that this is a little bit skewed. So maybe a sample of 25 is large enough, and our sample size of 312 is large enough. So we pass the nearly normal by way of large enough N right there. So a little bit of skew, but the large enough sample size means we're good enough on that. So make sure to include your output right there. Make sure to explain the conditions. And last but not least, we need to interpret the interval. So now we want to make a 99% confidence interval. So we go here to the red arrow, click confidence interval, and go to other for 99.99 right there. And we're doing the two-sided, and we're not using a known sigma. So here we are. I am 99.9% confident that the true mean age of UT students is contained in the interval 19.4 to 19.8. Kind of sounds accurate. And if you're really good, take a second and tell me what the margin of error is for 10,000 points. If anyone's listening, guesstimate the margin of error looking at this interval. So can you tell me the margin of error is about what for this interval? So can you look at it right here and be like, that's the estimate, that's the lower, that's the upper. Can you tell the margin of error? There's a lot of ways to find the margin of error. The margin of error is half the length of the interval, or it's from the center down to the lower, or the center to the upper. So what is the margin of error? The margin of error is plus or minus what? We'll see if anyone solves it right here. And we are on live chat. So the margin of error can be found by half the length of the interval. There's right there, 0.21, because think about it. 19.61 plus 0.21 is that value. Or if we're here at 19.61, we could subtract 0.21 and we'd be at the lower right there, 19.4. So the interval could be expressed as 19. Let's write this right here, 19.61 plus or minus 0.21 right there. And that is the margin of error right there. And what's interesting also is that's basically, we made 99.99. Yeah, so it's not going to be 2 times that. Good stuff right there. This is the data analytics. Make sure to interpret. I am 99.9% confident that the true mean age of UT students is contained in the interval 19.40698 to 19.82378. I would just write out all the numbers in my interpretation if Jump gives it to us. Let's do Taylor's question right here. We're planning to vote yes. We did that one earlier, Taylor, so we can come back to that. Taylor, if you're still here, let me show you where we did that one earlier, and we did a full walkthrough of it right here. Let me find it. We did that one today, right? 50, a city ballot includes, wait, a poll. City ballot includes, it's a city ballot, the city ballot, right? So we did that for 20. Let me show you where that's. I'm going to drop that link in the chat right here. So, and then we're going to do some support vector machine. So I'm going to drop the link in the chat. Here we go. Streamed 2 hours ago. Oh, let me put the timestamps in the video. And there it is right there. Now I can click the timestamps. Now it says HD below the video. That notation. All about notation. And there it is right there. So here is the question. I'm going to copy the link right here. And there's the question right there from earlier. Check it out. It's going to boil down to knowing the notation. The notation, the notation, the notation. Know your notation. So check out the notation right there. Let's do some support vector machine. Oh, we just did, confidence interval data analytics. Let's go check out some support vector machine. Can we possibly go over, have you done the routine screening? Let's do routine screening next. You got it, Merritt. Thank you for asking. How does the question start out? We might have done it. I can send you the link, but we do that one next. I don't see it today. I see a poll conducted, a consumer advocacy group, a city ballot, the environmental group, the housing market. I don't see it. Send me the start of the question. Here, we'll do it right after the support vector machine task 4. So during a routine screening, let's check it out. I think that one has to solve for the sample size, right? I think Taylor also has to have one, so that'd be good. I try to do as many different questions during the day as we can, so that way we can put as many new ones in the video. So that's why I want to make sure we get to Ella's question. So let's do that one right after this. I think Taylor asked that one earlier, so that's a really good one to do. That way we put out the most help. I know a lot of people use the videos later, so I try to mix it up with all the different questions right here. So let's see. We want to go to 474. BAS 474 and support vector machine. Thursday. That's the lab. What am I clicking on the lab for? And support vector machine. Homework on Sunday. Sunday homework night. Wait, Yes. Good. Homework file. Okay. A little advanced statistics right here. Let's go check it out. Here we are with the support vector machine assignment. So BAS 474, support vector machine task 4. Okay, let's check out task 4. Task 4. Okay. The class labels star or dot and two characteristics, x1 and x2 of the three individuals have been recorded. The data space with points encoded as their class labels is displayed below. Okay, woof, woof. A lot of stuff right there. So we have right here for it's going through a for loop and doing the it's a way to graph the normal. Let's run the plot. There we go. Wow. Okay. So this is a space that's perfectly defined right here. I think that's what it's getting at. Okay. Would logistic regression be an effective way to make classifications? Okay, so what does logistic regression fit on the curve? What does logistic regression fit on the curve? So this goes back to 320. Logistic regression fits a what on the curve? It fits a sigmoidal. So you have to think right here. So I don't want to go into too much detail. I mean, it says be as specific as possible. So if you look at these X's right here, do you think logistic regression fits the sigmoidal on the curve? And let's make... Oh, we don't want that. Maybe go behind. There we go. Yeah, so the sigmoidal, trying to describe this with the sigmoidal, really not going to help out much. It's really not going to work. So that's what they're getting at right there with that. Kind of answers own. Explain why the plot indicates that a vanilla partition model should do a good job. So if we go over here and look at the notes and look at how partition models work. So partition models, where's the partition model? Tree-based models, right? Tree-based models. Let me go grab the notes. Tree-based, there it is. Tree-based models. Okay. So here's the notes on tree-based models, and going in and looking at the vanilla partition model. Here is what we do with vanilla partition. So if you take a look at this right here, what are your thoughts? Like, does that... So Ella, does that make sense right there? Looking at it and thinking about how a tree-based model, a vanilla partition model, the way it's designed to do the segmenting of data, just kind of describing how it segments data and creates the rules right there is important to think about how it's creating the rules and what it's going to do. So we have here the idea of a logistic curve trying to describe the data. That's logistic regression right there, which is the GLM. So if we're predicting a categorical variable, GLM is going to do generalized linear models, which includes logistic. Don't think that's going to be a pro idea there, where tree-based models are going to use this. And this is just vanilla partition. Conceptually, is this making sense right here, Ella? Like, why? I don't want to quite say the answer, but when you think about applying this technique, which is the vanilla partition model, to this data, putting them in the same group through the partition, because the two darker dots are sectioned into... So we're trying to use some way to somehow put the dots together and the stars together. So it's kind of the same here. Like, these could be stars and these could be dots. Does that make sense, Ella? Like, these, for all intents and purposes, could be stars and these could be dots. And so it's the same sort of thing going on here where we have a two-class prediction. And so this is categorical, trying to reduce impurity. And so this is a categorical Y we're trying to predict, reduce impurity, and this is what partition models do. So I'm going to separate them from that node. Well, but then we would have three groups. Well, but then think about this. At the end of a partition model, can you have more than two groups? At the end of a partition model, can you have more than two groups? How many groups are there at the end of this partition model? Now, there's only two classes. So there's only two classes. But at the end of this, how many groups are there? Well, so, but how many groups are there at the end of this? How many groups are there at the end of this tree? How many groups are there at the end of this tree? How many leaves, so to say? Leaves are there's 4 leaves, right? So you can have more than well, so we're trying to get the stars together and the dots together. Does that make sense? You're trying to get these things all in one thing, and you're trying to get those. What is the impurity if this is how the model made? What is the impurity of this model right now? If we have here 9 leaves, what is the impurity? Calculate the impurity of this partition, right? Of this partition tree on the left. What is the impurity? Hint, it's the same as the one over here. It's 0. It has 0 impurity. Gini index or entropy would be 0 because everything's perfectly classified. So it's just doing the same sort of technique or visualizing the same idea of putting things into leaves, where the amount of leaves at the bottom is not how many variables there are, because we're still doing like a 2-class prediction right here. So it's still 2-class prediction with like, will someone buy the product? But we are trying to segment it into partitions where the partition idea is just dividing it within x's. Like we go within each leaf. This is a better way to represent it right here, where we make our first split dividing on x1 below this. Then we make our second split on x2 right here, which was within this split. So this is within the partition right here. So it might not exactly look like this, but the tree could do this. Yeah, so that's making sense how a tree works. So that's the tree-based model on a optional not graded. It's pretty. I think it's pretty easy to do. Like if you want to draw this out, it's not graded. Not graded. Why would we? No one's gonna do it. Here, I'll do it then. You ready? Tree-based model. Since it's not graded, I'm just gonna go ahead and do it. So, rule 1, x1 less than 4. Then within this, so you just go then subsplit within this. I guess you don't need to do that because you could just, that's fine right there. Oh no, it's gotta be easier. X2 greater than or equal to 6. That's first rule. And then, so that's going to split. Then this portion goes this way. We're left with this down here. So that's the first partition up there. And then this is x less than or equal to 6. So that's the way the tree split on the first. That's the x greater than or equal to 6, x2. And so if this is the right split, because that is going to be, no, this is the left split, because that's no. So within the left split now, we go here and we say x2 greater than, or let's say less than or equal to 4. And so x2 less than or equal to 4. And then this would be the yes is to the left. So we'd go to the right here. I can see why this is not graded. And then we go to the right here, and that means, wait, because whoops. Yeah, we have to split on the right again, so we're going to do that. Because now we're inside of this. And now we got to write an x1 rule. So now it's x1 less than or equal to 4. And if it's yes, it's going to be this portion right here is the yes now. So now we need to say the no. And so the no is over there. And we just need to split this one more time to say x1 is less than or equal to 6. And this is where all the stars are. So that'd be stars down here. Stars 100%. your stars. Right there. Does that make sense, Ella? So this is why we don't do this by hand, because sitting down, writing the rules out, just understanding what the techniques do is very important, but doing it by hand is just laborious. We can just ask it to do the work for us. It'll create the tree for us with the splits. 201, if you're watching, we use these techniques. This is the same old decision trees. Yeah, it's definitely time consuming. That's why we just have the tree do the work for us. And then we have to know if it's yes, it goes to the left, the question, right goes to the, no goes to the right. We talk about the upper level things in the upper level classes, like what is entropy, which is basically impurity or information lossage. We talk about Gini index, which is going to be the impurity, sums of squared errors, and understand how the trees are built and how they try to reduce impurity and how we can try to optimize our tree with the tuning parameters right there. So really good question. A lot of work right there to draw it out and draw the rules and to say if x2 is greater than this, x2 is less than this, x1 less than, x1 less than. It is getting warm today. I think it's warm outside and it's warm in here now. So I might need to turn down the hot air. I think we got the next question ready to go. The next question is during the routine screening. So 42, 33, stat 201, chapter 13 quiz. Let's go check it out. Okay, during the routine screening. During a routine screening. This is a tougher question, and I'll explain why. Here we go. Tough question right here, Meredith. Good job asking this one, because it's going to be tricky. Let's do it. So this question right here is another know your notation question, and is very, very tricky. Okay. So it asks, how many randomly selected adults would we need? So what is it going to ask us to solve for right here? It's asking how many randomly selected adults. That's the answer to the question is, how many randomly selected adults do we need? So we're going to solve for what? N. Great job, Meredith, right there. Keep up the great work. We're solving for N. So when it does this, it's going to give you some of the notation right here. We know from the formula p hat plus or minus z star p hat q hat over n square root. This is the formula for a one proportion z interval, for the true proportion, to estimate the true proportion. The margin of error is everything after the plus or minus, so this is the margin of error. We only are trying to solve for the margin of error here, so let's just write that is the margin of error. We already know that, so we're good to go. So it says they want a margin of error of 3%. They have estimated that, with 98% confidence, we'll use that here in a second, 98% confident, and she notices that 22%, 22%. So what else can I find right now? What else can I find? Do we have to get an 80 or higher now? Just start the. That is correct. It's been that way previously. You get one attempt at this quiz for free, and you have to get an 80 or higher on remaining attempts. What else can we solve for right now? What else can we solve for here? If we know p hat, we can solve for what? Anytime you know p hat, you can always solve for what? Because p hat is the percent in the sampler. She estimates it to be this. She's thinking it's about 22%. She wants to get a better estimate right here. So she has an estimate of her p hat, and her q hat, that's p hat right there, equals 0.22. There's a question that doesn't tell you it. Assume 0.05. If it doesn't tell you it, that question is tricky. So there's one that is very similar to this that you're about to see. So if you notice, we actually have everything we need. We have q hat. We have p hat. Now you can put everything in here and solve now, but I prefer to do the algebra. So I'm going to do a bunch of algebra right now to help out to solve this all. And here's how it works. Divide both sides by z to get z over here. That's the z star based on percent confidence. I'll show you how to get that in a moment. And then over here, you have square root p hat q hat over n. Now you square both sides, and square both sides. So that leaves p hat q hat over n. We don't want n on the bottom of the equation, so we're going to flip. You can flip both sides. Flipping both sides keeps it mathematically the same. So now we have flipped both sides, and it's the same algebraically. And now we're just going to multiply both sides by p hat q hat to get p hat times q hat times the quantity of z over margin of error squared equals to n. So now the only question here that we haven't solved for is, what is the z-score? Z-score is always relative to our what level? The z-score is always relative, and I'll show that math there again in a second. The z-score is always relative to our what level? So the z-score is always relative to, when we do, great job Meredith right there, the percent confidence. And notice how it has a star. It won't always have a star. Be very careful for later in the semester where we don't use z star, we just use z. We talked about that a tiny bit today where it doesn't have a star. Like over here, this one doesn't have a star. If it has a star, it's related to percent confident for intervals. So this one right here is the z star for a 98% confidence interval. So let's go over here and take a look at that. You have to go to the David M. Lane, which link is currently on the screen. Click the second button, type in 98%, make sure it's got z-scores for standard normal curve, mean of 0, standard deviation of 1, and it's 2.3263. The next digit's 3 right there. So that is the z-score we want right there, 2.326. And if you've done the algebra right here, we actually have the answer pretty much. We just need to plug in the values. It might be really zoomed out, but there's the equation on the bottom. So I'll write in green, 0.22 times 0.78. Oh my gosh. And z is 2. Make sure to do quantity squared. So here we are with 0.22 times, 0.22 times 0.78. And well, the other one's going to be more fun. 2.326 divided by 0.03. Square that times by the value we just found right here. And there it is right there, 1,032. Now make sure to round up. It does say round up. It's been a little bit nicer lately on it, but 1,032, make sure to round up, as in if it was 0.1, you would round up, or if this was the answer, you would round up. See how it says round up, so don't round it, round up. And we did the problem correctly. It's been nicer on this. It's given a little plus or minus on it. So that's nice that they finally added in a little margin of error on that one, just in case you might carry the decimals a little bit differently, or in case you don't round up. Probably they got lots of complaints from people like me, and they added in a little plus or minus. How's the problem going, Meredith? Does it make sense? This one really boils down to knowing all the notation for everything right here, like knowing your p hat, your q hat, your margin of error, how to find the z star based on percent confidence. We're solving for n, so don't plug everything in, just solve for n right here algebraically. And then you can rewrite the equation expressed for solved for n. And that will be the answer right there to plug in the 2.326 right there, the 0.03, the 0.22, and the 0.78. Plug those values into the equation that we have up above, and you have it solved. So really boils down to knowing the notation. We said all the time here. And what other questions are there? Really great work, everybody. Lots of really good questions. What other questions are there? Drop those questions in the chat as I reappear. Good stuff. Let's see. A lot of Discord stuff going on. We'll see if there's any more questions. A lot of work. And if you're checking it out, we've done a lot of the assignments, a lot of the questions, and really it boils down to knowing the notation. Know and practice your notation for every question. I know that's a lot, but write down what each one is. It's one thing to see me write them down and to repeat them, but have a notebook out and write down each bit of notation so that way you know what each one is. Oh man, that's awesome. That's the guy who joined our class really enjoyed it. It sounds like. Awesome. Good stuff. Well, any other last questions? Might end a little bit early. We've been going about an hour. We did morning office hours. Anyone here? Anybody here? Can anyone hear me? Hello? Hello? You're welcome, Meredith. Play one more song, chill out. Huge shout outs to Courtney of Haslam College of Business, Study Abroad. He had a great time joining our class today. So he gave a great presentation. So really, really great stuff. Send them the link. So glad he got to join in, give a great presentation, and really great opportunities to study abroad. Let me add in the class notes for it already. Adding in the notes. Notes for class. There we go. Afternoon, Shaq. Do you have any questions? What are you working on, Shaq? Let me know. Which question you want to do, Shaq? Let's do another one right here. Which one do you want to do? Just name a question that you're working on. Let's do it. Let's do that question. Woo. Notation, notation, notation. Here's the thing. Remember, start early. Ask the questions. You got this, Shaq. Which one we doing? You name it. Let's do it right now. Which one we gonna do? Name it. Whatever it is, even if we've already done it, let's knock it out. Let's do it. Let's do that question. Let's review that question. I'm disappearing. Whichever question's on your screen right now, just name it. And let's get the question done. Which one are you taking a look at? Context bugging me. We'll go to this main screen. Pew Research. Pew Research right here. Pew Research. So we got Pew Research right here. I think this is it, right? Is this it right here? Is it a little bit different? Wait, no, is it right here? Here we go. Pew Research 2018. Okay. Let's put it in the video. Thank you, Shaq, for being here. Throw some points in a second. So... What? There we go. Okay, you ready? Interpret the interval. Okay, how do we usually start out? Give me the first two words of how I usually interpret this. Don't worry about what they write. Practice for yourself right here. The first two words of how I interpret it. So I'm going to give you my interpretation in a second, but just give me the first two words to make sure. If you don't know, that's all right too. But what are the first two words I always use when I interpret the interval? I'll show it here in a second. But do you remember the first two words that I use? To talk about how confident I am. How do I always start out? Every time you hear me interpret an interval, I'm going to do it the same way. So practice. No worries, Jack. I'll throw you 1,000 points for training you forgot. We're here to practice. That's what we like to do. I say I am blank % confident that the true blank is contained in the interval blank to blank. So here we are. Here's the interpretations. Make sure to write them down. You'll need the context. I am blank % confident that the true blank is contained in the interval blank to blank. And then for hypothesis testing, which we'll get to next class, with a p-value of blank, I reject or fail to reject the null at the blank alpha level. This means I do or do not have evidence for my alternative, that, and then give the context. So we need to look for something similar, like I am or one is blank % confident. We want to talk about the truth though. One is 95% confident that if we were to ask all teens, which means the truth for everybody, whether they go online several times a day, between 42 to 48% of them would say they do. So that kind of sounds like it. I am 95% confident the true proportion of teens who go online daily is contained in this interval. Now, here's a really good question, Shaq, for another 1,000 points. What is the margin of error of this interval? So that's the answer right there. I am 95% confident that the true proportion of teens who go online daily is contained in the interval 42 to 48. This survey sounds old. What is the margin of error? Good to see you here, Noah. What is the margin of error of that interval? So see if you can calculate it like that. Not what, good guess. It's going to be, think of the margin of error is always what of the interval. If you think about a margin of error, the margin of error looks the following way. The margin of error is always half the length of the interval. So since the margin of error is half the length of the interval, what is half the length of that interval? As in, we could say 45% plus or minus what? So the margin of error is always half the length of the interval. This interval could be stated as 45 plus or minus what? 3%. Great job, Shaq, right there. And notice how that's 3% here, plus and minus. So a formula can be upper minus lower divided by 2 for the margin of error. If you want to do that, you're just figuring out how long the interval is. 48 minus 42 divided by 2, half the length of the interval. It doesn't ask that, but we should know things like that when solving these problems to figure out the margin of error. Explain 95% context. Yeah, no, this is, Shaq, here's the thing. When you get to the test, now you're like, oh, margin of error is easy. It's just half the length of the interval. How long is the interval? Cut it in half. Margin of error. If a question says, what's the margin of error? You're like, oh, it's just half the length of the interval. It's the plus or minus. It's up this much, down this much. So it's the interval cut in half. So if you practice that and know it, you get to a test question, you're like, well, that's easy. I've had people be like, I don't have a formula. I don't have the S. I don't have the N. I don't have the T. And I'm like, well, what is margin of error? And they're like, it's T, because I feel so bad, because a lot of times students will be looking at the interval and they'll say, well, the formula is P hat plus or minus Z star P hat Q hat over N square root. And they'll say, if I need to solve I had a student who was really very, very, they were looking, they were like, okay, so how do I get the margin of error? And I was like, well, you know the interval. And they were like, yeah. And they're like, well, what's P hat? And you could find P hat from the interval because it's the center of the interval. P hat would technically be upper plus lower divided by 2. That's where the center of the interval is. So the center of the interval is the average of the two, like 42 and 48 average to the center. But then they're like, what's the sample size? And I was like, well, you don't need that. And then they were like, well, what's the Z? And I was like, well, you don't need that. And they're like, no, you have to with the formula. And I was like, you can find margin of error. And they're like, no, I don't have what I need. And I was like, well, you do. And I was like, I can tell you after the test. And they're like, well, can you tell me what Z is? And I was like, not for this question though. They're like, well, then I can't solve it. And I was like, I felt so bad. I was like, no, you can still solve it. It's half the. I didn't say that. I can't say it like, during a test. I can't say it's half the length of the interval. Yeah, no, it's all right, and it's all right once you know it. It's like, oh, I think they said that. I just remember it was in the alumni memorial auditorium, and I just remember they were on the front left row. I got a very visual memory. I just remember them being like, no, I can't solve it, and I was like, oh, yeah, you can. I promise. Explain the meaning of 95%. 95% means 95% of 95% confidence intervals are expected to contain the truth 95% of the time. So that's what we mean when we say we make a 95% confidence interval. It's not about one interval containing the truth. It's about the process of 95% confidence intervals. 95% of 95% confidence intervals are expected to contain the truth. So there is about if you collected many random samples, as in many random confidence intervals, about 95% of the confidence intervals constructed would contain the truth. So about 95% of 95% confidence intervals contain the truth. Shaq, which one do you want to do next? That was a good question right there. That is part of the theory. It's not about one interval having a 95% probability of containing the truth. It's about the repeated process of making intervals that 95% of 95% confidence intervals in the long run are expected to contain the truth. So 95% of 95% confidence intervals are expected to contain the truth. So it's not that one interval has a 95% chance. All of these are wrong interpretations here that have, like, let's read the first one. There's about a 95% chance we don't talk that way, that the true portion of all teens admitted to going several times is contained within the bounds of the interval. No, it's about not one interval. It's about the creation of multiple intervals in the long run. And you see that right here by showing in the long run. So it deals with the law of large numbers right there. Then in the long run, we see 95% of 95% confidence intervals contain the truth. If one were to collect many random samples of teens, about 95% of the confidence intervals would contain the true sample proportion. No, we're not trying to find the true sample. We're trying to find the true proportion for the population. So if this said true population proportion, that's what truth is. Then be careful. They switch up where the spots are. This says sample right here, and we're not trying to find the true sample. We know what the sample proportion is. That's actually the center of the interval. The center of the interval is actually where p hat is at, so we know what the sample proportion is. So we're not trying to find that. The interval tries to estimate the truth, which is for a population. So if it said true population proportion, that'd be correct. There's about a 95% chance that the true proportion of all teens who admitted going several times days is not contained. Well, no, it's just the reverse of this, which is wrong. But then this doesn't even talk about what we're trying to estimate. So good question. Reading over the wrong interpretations, knowing why they're wrong is important. Maybe that's a tricky one right there. Direct mailing, yeah, let's look at that one. That one has very small numbers. So this one right here, Shaq, has very small numbers. So I really like solving this one. I'll show you a trick, and we'll see if we get it right. I wonder if they've done this. So let's go. I think it's towards the end of here. Direct mailing. It'd be funny if I got it. Direct mailing. This has very small numbers. Here it is. I've done this one a lot. You can't tell. Step 201, chapter 13 quiz. Here we go. So in this problem, what do you need to know first, Shaq? What do we always do when we get to a problem, especially for the last test? Immediately channel your inner Leo, and we're going to find the what, Shaq?
Notation, brother.
I hear Leo all the time. I hear Leo all the time. What are we going to find? What are we going to find to start? That notation, brother.
Notation, brother.
There we go. Notation, brother. He beat me to it. Leo's always there for us. So when we find this notation, we're going to be solving the following formula. If you know the formula, it can also help. Be careful. You might choose the wrong formula, which means you're going to go down a wrong path on looking for notation. So a lot of times I like to try to find the notation first, and then it's going to help me find the formula, because you know right now you're in chapter 13, so you know which formulas to use. But on the test, you might not know which chapter you're doing, so you'd want to identify the notation. As in, the amount they send out as a sample is going to be, here we go. They send flyers, send it to 10,040 people. They get orders back from 1,049. Now, you have to be careful. 149, not 1,049, is what? This is N. The 149 is what? Be very careful. The 149 is what? The 149 is what? I'm going to Google something in the background. Not quite. And so P hat, good answer, Shaq, right there. P hat will always be a what? Generally is a what? Because P hat is a proportion. P hat is probably going to be between what and what. If we find P hat, it's probably going to be between what and what. Now, this will help us find P hat. But P hat's probably going to be between what and what. So that's the amount of people who responded in the affirmative. P hat is a proportion, so P hat has to be between 0 and 1. Does that make sense? Or we could express it as a percent, like 20%, which would be 0.2. So P hat has to be between 0 and 1, or expressed as a percent, because it's a proportion out of the total. So this is actually X. And how do we solve for P hat, which comes from this? How would you use those values to solve for P hat? To remember, P hat is the proportion of successes. And we know how many successes there are and the total amount we sent it out to. So how can we figure out the proportion of successes? Because we know 149 people responded out of the 1040. So what is the formula for P hat, which is the amount of successes out of the sample? X being successes, N being sample size. What is the formula for P hat? Exactly. X over N equals P hat. And once you find P hat, what do you always solve for next? Once you solve P hat, you solve for what next? You solve for P hat. What do you get next? Q hat, exactly. Now they have hats because they're from samples. So do remember that. P hat is going to be, really? There we go. P hat is going to be that. Q hat, they come from samples. They're not the truth. If it's Q, it's the true complement of the proportion, the true proportion. But this is the complement of the sample proportion, which would be 0.8568. Double check your math. You can do it in your head for funsies, but then double check it right here and make sure you have it. That does, I must not have rounded the other one properly. I don't think it's going to make much difference on the last decimal, but let's be careful right there. There we go. So double check. We have P hat, we have Q hat. So now we have a lot of the work right here. We have P hat. What are we missing? What component are we missing to create our confidence interval, and how are we going to find that? So what component are we still missing? We're still missing one component right here, and what is it? What are we still missing mathematically? We're still missing what? What are we still missing? Z, and the Z star technically. So how do we find Z star? How do we find that one? So we've got everything but our Z star to solve this. How do we get that one? How do we find the Z star? That's based, it's got the star because it's based on a certain what? We need a little more info right here. It has a star because it's based on a certain what? It has a star because it's based on a certain confidence level. Confidence level. Good work and good practice, Shaq, right there. Based on a confidence level. So whenever you see Z star or T star, that means relative to a certain confidence, and you pick the one based on that. Be very careful, and I want to mention this again. Later in the semester, you will not see stars on them because we'll be doing formulas where we'll solve for T or Z. Notice how none of these T's or Z's on the screen have stars because we're solving for them. Notice how the ones up here have stars because they're used for intervals. So the intervals have the stars because you're solving based on the percent confidence, where the tests, which we'll talk more about next class, do not have the stars because we're going to solve for the standardized difference. So the T right there will be a standardized difference rather than a T or Z relative to a percent confidence. So we have to go over to the David M. Lane to get this. The Z score for a 95% confidence interval is the classic 1.96. So there's the David M. Lane right here. And let me show you from scratch here how to get to it. We'll load up Scratch, click this button, put in 95%, and then go to the between, and you've created 95% shaded in the middle, and the Z score is 1.96. It'll do the plus or minus for you. So now we just plug in our numbers. We're good to go. There we go. And so 0.1433 plus or minus 1.96 square root. And there we go. Everything after here is the margin of error. Make sure to know that. The margin of error has two components. It is the standard error and also the confidence level right here, which is the critical value. So that's the confidence value or critical value. And this is the standard error component right here. Multiplying them together does make the margin of error. Very important stuff to know. And so let's go ahead and take 1 minus, there's that, times this, divided by 1040. Here is the standard error right there. That is the calculation for that quantity. Times by 1.96 is the margin of error. So 0.0213. And there's the confidence interval right there, or there's the values. It wants it as a percent, so let's times it by 100. And then we're going to add and subtract the values right here. That's 16.46. And then the lower value is going to be 14.33 minus 12.20. There we go. How's it looking, Shaq? How's the problem working out for you? Those are the values right there for 95% confidence. Got to make sure you choose the right. If it's not 95% confident, watch out. You want to make sure you pick the right values. Which one? What are you left behind? Which part are you wondering about right here? So identify all the notation and then plug it into the formula right here. So you want to identify your P hat, Q hat, N, Z, and P hat. So here I'll highlight here. So there's the P hat. Here's the Z. So then it comes down to solving the algebra. Do you want me to solve the numbers again? So now it comes down to solve the algebra out for the... Here's the margin of error. What can I do to help out, Check? Let me know. There's the numbers plugged in. Make sure to identify your numbers in your problem and solve for the values. You think you got the wrong number for your lower value? So tell me this. Tell me your numbers here. Do this, Shaq. You ready? What is your X for this? What is your X? What is your value of X? So go ahead and tell me what your X was for that problem. 150. What is your sample size? And then is it 95% confident? Yes or no? Because this does 95% by default. Is it 95% confident? Okay. So are your values about 11 to 15%? That's this. If you tell me what your upper is. Oh, that sounds like your margin of error. That sounds like your margin of error. That's your margin of error right there. The margin of error, I think you solved for margin of error. So that's this value right here is the plus or minus that. So that's the margin of error. Does that make sense? This is your margin. That's not the upper. That's the margin of error. So this is 14.33 plus or minus, and yours looks to be about 2.06. And there's your lower. Does that make sense? Does that help to see it like this? And do you see what I've done right there? So hopefully seeing it on the screen better than my handwriting. Sometimes I use R, like I want it to help out. I can also use it to kind of check your work by doing the confidence interval here. Don't use those values. Use these values, which are virtually identical. But if that is your margin of error that you calculated, 0.0206, then, and so that should be right there. How's that looking right there? Those should be the values. That should be... So then times it by 100, though. Make sure times by 100, round to whatever it says. We store into X. X, or we could say low here. What is that, low or high? It's high and low. And then round, join, low, high to 2 decimals. They're right there. That's why I love coding. Just store your stuff, round your stuff. You don't have to think. You just code and it does the work for you. So we just round and turn them percentages, all that good stuff right there. 12.2 to 16.46. So 12 point, round to 1 decimal. 16.46 is that. So make sure to round to 1 decimal. There you go. 10.9 to 15.0. Should be right. If your margin of error was correct, should have it. So once again, how do we start our thing here when we interpret, Shaq, the confidence interval? How do we start? I want you to give me the first 3 words of your confidence interval interpretation that you'll be writing on the test. Don't look at theirs. Know how to do it. Know how to practice it. Be ready to write confidence interval interpretation on the test. Give me the first 3 words of it. I am. And then we give the blank percent confident. Shaq, great job right there. I am blank percent confident. You're right. I am blank percent confident that the true blank is contained in the interval blank to blank. So right here, I am blank percent confident that the true either mean, proportion, or difference between means. So these are different chapters right here. And then give the context of it. Is contained in the interval lower to upper. And those are the 4 parts. I think of it as 3 a lot of times. The company is 95% confident that the percentage of people who will respond, because that's what they're trying to understand, that's the context, falls within the interval. Don't love that, but it's not the randomly sampled people. It's the company is trying to estimate the true proportion of people who will respond to the flyer. I don't like the word falls because that's active on the truth. It's that the interval would contain the truth. Explain what 95% confidence means. 95% confident is about the process of making the intervals, as in we are 95% of 95% confidence intervals are expected to contain the truth in the long run. So it's about the law of large numbers here, that one interval itself might or might not contain the truth. That's just a fact of life. But in the long run, the repeated process of making the intervals will see that 95% of 95% confidence intervals are expected to contain the truth. So about 95% of random sample sizes of 20, 10, 40 will produce confidence intervals that contain the truth. So about 95% of the 95% confidence intervals produced will contain the truth. The company must decide to do the mass mailer. They will do the mass. The mailing won't be cost effective unless at least 6% return it. What do you think? Do you think at least 6% will return it? What do you think, Shaq? Looking at this interval, would you say to the company, do the mailer or don't do it? Do you think we have evidence that at least 6% will return this? Because we're going to send it out to everybody. And we sent it out to these people, and we estimate somewhere between 12.2 to 16.5% of everybody will return this. Do you think we should do it? Do you think at least 6% will return it? What do you think? Well, so 6 is not in here, right? The interval is entirely where? So I think somewhere between 12.2 to 16.5% will return it. The interval is entirely what to 6%? Now, the company wants people to return it. They want them to do this, respond to it. So the interval is entirely what to 6%? The interval is entirely what to 6%? It's entirely what to it? Because we think somewhere between 12.2 to 16.5. The interval's entirely where to it? 6%'s down here. The interval's over here. So we don't think 6% will happen. It's much higher, right? So the return is higher than they want. So should they do it? Yes, or should they do it? No. The return is higher than they want, and they want return. So they're saying we need at least 6% to do this. Do you think we'll get that? And what would I say to them as a statistics person? They're saying, do you think we'll get at least 6%? And I would say, well, yeah, do it, right? Because we think probably between 12.2 to 16.5% of people with 95% confidence will respond to this. So I'd be like, yeah, I'd say go do it. So do the mass mailing. Yeah, do it. Probably going to get that return. Woo! Another 100. Good stuff. We're on a roll. Shouldn't jinx us. So with that, we might end off right here. Shaq, how's it doing? Is it going better? Check out, we've done a lot of the other questions on different things right here. We did some this morning, different quiz questions here. Those are already marked. I didn't mark them yet. I'll mark them here soon. But we've got some questions in the morning video. We've got some questions in the afternoon video. It boils down to notation, 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 notation. All the notation. Looking good. Those were my 2 hardest. Great job. And there's tricky ones here, like the routine screening one. But keep working hard, Shaq. Keep up the great work. You got this. Let me know if you have questions. Bye for now, everyone. Bye.